Section 2.5, Physical Applications. So as we've done previously, we are going to create a Riemann sum. Okay, so in this case, we're going to be finding mass. So we are going to take the mass of a slice, and we will sum it. Okay, so that's where our Riemann sum is going to come in. Our infinite number of tiny, tiny slices. So the total mass is determined by the density of the object multiplied by the length. Okay, and that's going to be for our slice. So I have total mass here, but really you can think of that as how we're going to find the slice itself. Alright, so mass density formula of a one-dimensional object. Given a thin rod oriented along the x-axis over the interval from A to B, let rho of x, this is the Greek letter rho, it looks like a P, okay, let rho of x denote a linear density function, giving the density of the rod at a point x in the interval. So we have a variable density as we're going, okay. The density is different at each point, and we have a function that represents that. So then the mass of the rod is given by m equals the integral from A to B of the density function rho of x dx. So to begin with, we have a thin rod oriented on the x-axis, and it's on the interval pi over 2 to pi. If the density function is given by rho of x equals sine x, what is the mass? Well, based on the formula we have, this is our variable density function, so the mass is equal to the integral from pi over 2 to pi of sine x dx, okay, where that is rho of x. Alright, well, that is a simple calculation there. We can make sure that that is negative cosine x, that is the antiderivative of sine x, and evaluate that from pi over 2 to pi. Now, I'm going to leave the algebra there, the evaluation, to you, but this actually, believe it or not, comes out to be 1. Okay? So the mass is 1. Now, we're not given units here, but generally, mass is going to be in kilograms or grams. Okay, so we don't need units there because we weren't told what the density function was, or what the units were for that. Okay, next, consider a thin rod oriented on the x-axis over the interval 1 to 3. If the density of the rod is given by rho of x equals 2x squared plus 3, what's the mass? Well, again, based on our formula, our mass is the integral from A to B, so from 1 to 3, of rho of x, 2x squared plus 3, dx. Now that quantity is our integrand there. Alright, well, that is going to integrate as 2/3 x cubed, using our inverse power rule, plus 3x evaluated from 1 to 3. And again, the algebra is up to you, the plugging that in, and this should be 70 over 3. And of course, as you're going through this, make sure that you are pausing, rewinding, because that's the way you're going to make sure you get it, and checking these things as you go. So don't just write down blindly what I write. There could very well be a mistake. I'm hoping there isn't, but there could be. So keep that in mind as you're going. All right, and again, every page is going to have this on here, but download for free at this URL here is where you can download all this information, because it is from OpenStax Calculus Volume 2, okay, which is free and open source. You can get a copy as many times as you want. All right, so next we're going to consider a circular object rather than a rod. So previously, I didn't draw this, but really the mass is we have a thin object, a thin rod like this, okay. Now I have to draw it like it has some width, but really it's very thin. Okay, the next thing we have is a circular object rather than a rod. So imagine a metal plate that looks like so. It's a circular object. Well, then the mass is calculated by calculating some individual strips. Okay, so we have a strip right here. We've got a strip right here between there. We have another strip here, and by calculating each of these tiny, tiny strips and working from the origin and coming out, okay, that's how we're going to find the mass of that plate. All right, so the equation, or the formula, this is going to come from a Riemann sum that we could write together, but the mass density formula, if it's a circular object, is if rho of x is an integrable function representing the radial density, okay, so the density based on the radius, because it is a circle, of a disk of radius r, then the mass of the disk is the integral from 0 to r, that radius of the disk, 2 pi x rho x. Alright, so this would be the way we would find the perimeter, the circumference of the circle. The circumference of each of those individual disks over that density function, okay, and then we're integrating that from 0 to r. Okay, so let's apply that equation here. Let rho of x equals square root of x represent the radial density of a disk. Calculate the mass of radius 4. So our integral is going to be, our mass equals integral from 0 to 4 of, and we're going to have 2 pi x times rho of x. Now rho of x is the square root of x in this case. And we need to make sure we have our dx there. Okay. Now, this can be written then as the integral from 0 to 4, 2 pi x to the 3 over 2. Because the square root of x is just to the 1/2 power. Okay, so we can combine it that way. Now, this is where I'm going to leave some more of that Calculus 1 material, the evaluating of the integral. Since this is just the power rule, I'm going to leave that to you. And this should be 128 pi over 5, okay, which is a very strange number, but if you do calculate this, that is what you should get. And of course, remember, you can actually factor out the 2 pi, so you don't have to worry about that as you go either. All right, next question. Let rho of x equal 3x plus 2, and that is the density function for the radial density of this disk. That didn't make sense. That is the radial density of the disk. Okay, and that's the function to represent that. Calculate the mass of the disk of radius 2. Applying our equation, that is the integral from 0 to r, our radius is 2, of 2 pi x, and our function is 3x plus 2 dx. That's our density. Okay, I'll go ahead and work this one out just a little bit. From 0 to 2, and I'm going to factor out my 2 pi. Not going to worry about that. Now, multiplying in my x, that will be 3x squared plus 2x dx, which will then become 2 pi, and the integral of that is x cubed, the antiderivative, x cubed plus x squared, and that is evaluated from 0 to 2. Okay. Doing the evaluation and keeping the 2 pi, keeping in mind that, we are going to get, well actually we're going to get 2 pi times 12. So our answer there is 24 pi. And I'll say it again, check me as you go. Make sure you understand each step of each problem, and if you don't, pause it and rewind it. That's the beauty of a video. Alright, we will move on from these thin circular objects, thin rods. We're going to move on from there to something in physics. Okay, and most of this is going to be physics. It's physical applications after all. So in physics, work is something that we talk about, and it's force applied to an object as it displaced. So force over a distance. Okay, so generally the way we calculate that is force is the distance multiplied, work, I'm going to write it this way, work equals force times distance is generally the formula we will use with that. Okay. So we can calculate it by using that formula. Now, as an integral, we are going to individually add up the work done at individual points and then sum those up. Okay, I'm not going to show you the Riemann sum here, but really it's this. From I is 1 to n of our force, F of xi, times di, the distance, and then we take the limit. So I guess I lied. I am showing you the Riemann sum there. But as we take that limit, if you notice, what happens is the f of xi becomes the function f of x. The di, the distance of displacement, becomes dx. And then we end up summing along that integral from a to b. So we have the integral from a to b of f of x dx. All right, so let's look at an example of this. So first we're going to consider a block attached to a spring. Okay, so here we are. It's on a frictionless surface. A box attached to a spring. This would be equilibrium right here. Okay, because that is where That is where it's resting. Okay. Now, if we push that block in, okay, to where x is less than 0, then that would be a compression. Okay, that's important. X is less than 0 with a compression. If we pull it away from equilibrium, that is a stretch. Okay, we are stretching our spring. Okay, so in particular with springs, we have something called Hooke's law, which says that the force required to compress or stretch a spring from equilibrium position is given by f of x equals kx for some constant k. So the k is going to depend on the spring. It's called a spring constant. Okay, so the first thing we're going to actually have to do is find what the spring constant is for this example here. But remember, we have f of x equals kx. Okay, so example 40, suppose it takes a force of 10 newtons in the negative direction, okay, to compress a spring. So the compression is what makes our x less than 0. And we're compressing the spring 0.2 meters from the equilibrium position. How much work is done to stretch the spring 0.5 meters from the equilibrium position? Okay, so first I'm going to take this function, f of x equals kx. We need to find out what k is. Now we are given a force that is 10 newtons, and because it is compression, I don't need to write the units there. Because it's compression, I have a negative force, and we don't know our spring constant, and the distance it's compressed is 0.2, so negative 0.2. Alright, solving that, we find that k equals 50. So our force function is 50x. Okay, now what we've really been asked to do is find the work. Okay, so the work is going to be the force times the distance. Okay, so the integral, and here we are stretching it 0.5 meters. So we're starting at equilibrium, moving to 0.5 meters. And we are working with the force function 50x, and the distance is dx. Okay, so force times distance for work. Alright, so integrating that, we get 25x squared, the antiderivative there. 25x squared evaluated from 0 to 0.5. And that is going to be, most importantly, what the units are, but it's going to be 6.25 joules. Okay, so work is going to have units of joules in the metric system. We have something called foot-pounds when we get into the customary system. Okay, so our units are joules, which joules are, I believe it's newtons over meters cubed. So it all has to do with, because they are those metric units. Okay. Alright, so next, same idea. Suppose it takes a force of 8 pounds. Okay, of 8 pounds to stretch a spring 6 inches from the equilibrium position. How much work is done to stretch the spring 1 foot from the equilibrium position? Alright, so let's see what we've got here. So first we need to find our force function. So our force is kx. So the force is 8 pounds. And I'm going to go ahead and convert this from 6 inches into feet, because that is the standard that we're going to use. So this is 0.5 times k. Solving that, our spring constant should be 16. Alright, so if our spring constant is 16, our function is f of x equals 16x. Alright, now to find our work, that is the integral from 0, we are stretching 1 foot. So for integral from 0 to 1 of our force, 16x, that's our force function, times our distance, which is dx. Okay, finding the antiderivative there, we get 8x squared, evaluated from 0 to 1, which is going to be 8. So because we were dealing with feet and pounds, our answer is in foot-pounds. There's a good chance you'll hardly ever have to worry about the actual units because XYZ does give that to you, generally speaking. But if it ever wants you to put that in, remember they are in joules if they are metric. So metric is in joules. Customary, which means we have foot, feet, and pounds. That's going to be foot-pounds. Sort of makes sense. Alright, next thing we've got is more work. So we still need this statement. I'm going to write this here first. Work equals force times distance. We will need that. Alright, so we're going to consider the work done to pump water out of a tank. Okay, the concept is the same. Work is force applied over a distance. But the force is what changes. We need to find a force function for us. Alright, so consider this example. Determine the work done to pump water out of this tank. Okay, so let's just give it a second and stare at this and figure out what we know about this. Well, first, x equals 0 is considered the top of the tank, and x equals 10 is the bottom of the tank. Okay, but our x-axis is going, our values are going down in this manner. Okay, we have a tank of radius 4. Okay, and there's actually 8 meters worth of water in here. Alright, so one thing we're going to need to know is the weight density of water, because we've talked about the weight density function, okay, but this water is uniform. Okay, so the weight density of water is 62.4. Okay, so our rho is 62.4 pounds per foot cubed. Okay, or 9,800 newtons per meters cubed. So I could have been wrong on that conversion earlier, actually. Did you check that?
The number of the units.
Units.
The units. 1 joule is a kilogram times meter squared over second squared.
Kilograms. Joules is kilograms times meter squared over second squared. Okay, so I was very off. I was thinking about the weight density there. Okay, so that's what a joule represents, based on the topics we're using in there. Okay, so if we need the weight density for water, which we will, it's one of those two depending on what system we're using. So if you're looking at this one, notice that we have meters. Meters everywhere. So we are going to use joules for our work, and we are going to use 9,800 for our weight density. Okay, so because looking at this tank, if I am thinking, okay, what is the weight of one single slice of that water? If I'm thinking one slice of that water, I would find it, because this is a cylindrical tank, I would use the function pi r squared. All right, so my work is going to be the force, okay, which in this case, the force is actually the weight of the water. It's the weight of the water. So it is rho pi r squared. And think about that. We're trying to push this water out. So the weight of the water is what we have to push to get it out. Okay, so rho pi r squared, density times the volume of that water, okay, and of that disk, and then that's the integral of x dx. Okay, that is going to be our distance, okay, because this is actually the height, and the height of the water is what is changing. Okay, and we are wanting to do this from 2 to 10. Because the top of the water at this point, the top of the water is at 2. It's because 0 is starting here, and we are going down to a depth of 10. So we're evaluating this from 2 to 10. Alright, now let's fill in the information we know. Rho is 9,800. I'm not going to worry about the units here. Alright, pi r squared. Our radius is 4 squared. Integral from 2 to 10 of x dx. So the force actually with this container of the cylinder, the weight of the water isn't changing, so our force actually isn't changing. Alright, so that would give us 156,800 pi, if we calculate that part, times the integral from 2 to 10 of x dx. That integral will be x squared over 2, evaluated from 2 to 10, 156,800 pi. And the evaluation gives us 7526400 pi joules. So that is 7 million pi joules to force that water out of that tank. Okay, so in general, solving a pumping problem, okay, the plan is going to be to first sketch a picture of the tank and get an appropriate frame of reference. That is, our x's, in our case, we're starting from the top and going down. Okay, calculate the volume of a representative layer of water. Multiply the volume. Okay, so for us, that was the pi r squared. Okay, so the volume of that is pi r squared. Multiply by the weight density function, so rho pi r squared. Calculate the distance the layer of the water must be lifted. Well, it's actually going from 2 to 10 in our last case. Okay, multiply the force and the distance to get an estimate of the work needed to lift the layer of water. Okay, so we got, let's see, that would be rho pi r squared times x. Okay, now our distance is really the 2 to 10, so that'll come in with our integral. And let's see, sum the work. That's where the integral comes in. The distance was from 2 to 10. From 2 to 10. And the x dx is where that comes in. And once we take the limit, that is the function that we get, okay, with something like that. So sketch it, figure out what's going on, figure out the volume of a particular layer of water, and then that's where our integral is going to come in. And the x is going to be the distance that we're traveling, so we have to make sure that we include that. Okay, number 43. Assume a tank in the shape of an inverted cone, with a height of 12 feet and a base radius of 4 feet. The tank is full to start with, and water is pumped over the upper edge of the tank until the height of the water remaining is 4 feet. How much work is required to pump out that amount of water? First thing on our list is sketch a picture and make sure we have a frame of reference. Okay, so if I sketch my cone, it's an inverted cone, so I've actually got this going on. Okay, I'm just drawing that because it is a right cone. Because we have a height and a base radius, so we have got a radius of 4. Do that in blue. Okay, our radius is 4 at that point. The height is 12. And notice these are in feet. Alright, and then we are pumping water. And we want to know when let's see, until the upper edge of the tank, until the height of the water remaining is 4 feet. Okay, so we're really concerned with this position here. And I don't know what the radius is there, which I'm going to have to find out. Okay, so how much work is done? So first, I'm going to need to find out a representative layer of this water. Okay, so a representative layer of that water. Well, it's going to be a circle with a certain radius. Okay, so that's the part that I need to find out. So what I really need to know is what the radius is right here. Now the problem is that depends on how deep or how much of the water you've pushed up. Okay, depends on the depth. So what I'm going to do is I'm going to use a similar triangle. Make that bigger. I'm going to draw two similar triangles because we have this right cylindrical cone. Okay, a radius of 4 gives a height of 12 total. Okay, that means that at a depth of x, okay, that leaves 12 minus x below. At a depth x, we need to find out what the radius is at that point. Okay, so hopefully you can see what's going on there. Okay, so pause, rewind, and listen, hear me say that again. So we have a similar triangle. A radius of 4 gives us a depth of 12, which means that at a depth of x, we have a radius of r. Okay, and that puts x and 12 minus x here. Okay, so similar triangles means that we've got r over 12 minus x, okay, proportionally. R to 12 minus x is congruent or equal to 4 over x. Okay. Now, since we're starting at the bottom, we're going to go ahead and make that x. The depth we're concerned with is 12. Okay. So the radius is 4. The height is 12. Okay, that's this part right here. The radius is r, the depth is 12 minus x. So if we use some algebra here, multiply this across, we get 12r equals 48 minus 4x. Dividing by 12, our radius at a depth of x is going to be 4 minus x over 3, or 1/3 x. So to find the volume of our representative slice there, okay, we need to know that it had this radius function. Okay, the volume of that representative slice is pi r squared h. So pi, our r is 4 minus 1/3 x squared, and our height is dx, or delta x. Alright, so our force is then going to be 62.4. There's our weight of our water, times pi 4 minus 1/3 x squared dx. And the depth is going from 0 to 8, because we want to know when there is 4 left. So the height remaining would be 8. Okay, so that would be approximately, well, that would be equal to, actually, it would be equal to 10,649.6 pi, which is approximately 456.7 foot-pounds. Okay, now we are following those steps, but one important thing, particularly when you have something like this, is congruent triangles. Okay, the idea that we can use similar triangles on that, and we are going to use that at least 2 more times in these notes. Okay, we don't have that much more to cover, but we are going to use similar triangles for every one of the ones we have left. Okay, the last application in this section is something called hydrostatic force. That is force that's exerted on an object when it's submerged in water. Okay, when you push something down into the water pushes back. Okay, and so that's how we would measure this. Okay, so what we are going to do is, if we have a force with a variable width and a variable depth, okay, then our force is given by F equals the integral from A to B of rho, that is the weight density of the water, W of x, okay, which is going to be a width function, and times S of x, which is the depth function. Okay, so let's jump in the problem and see if we can make sense of this. All right, so first we're going to want to sketch a picture and get an appropriate frame of reference. Then, of course, we want to determine the depth and the width functions, the S of x and the W of x. Determine the weight density of whatever liquid. For us, I think all the time we're going to be dealing with water, so it's 62.4 pounds per foot cubed, or 9,800 newtons per meters cubed. And then we'll use that equation to calculate our force, the equation we were given. All right, so a water trough, 15 feet long, has ends shaped like inverted isosceles triangles. Okay, so we've got, there's our end, we've got our our trough. Okay, so it's 15 feet long. That's worth noting, I think. All right, with a base of 8 and a height of 3. Okay, so the base is 8 and the height is 3 feet. Find the force on one end if the trough is full of water. Okay, well, first our depth function. Let's go ahead and aim for that. The depth function, S of x. Well, the depth is just the depth. Okay, that's how we're measuring everything. So S of x is actually x, because our depth is just going down. Okay, our width function is a little bit trickier. So let's look at rho. This is in feet, so this is going to be 62.4 pounds per feet cubed. Okay, the width function. So at a particular depth, we need to know what the width of that triangle is. In fact, we don't care about the whole rest of this. All we really care about is the end, because we're finding the force on one end. Okay, so we have got something that looks like this. Okay, we have got a base of 8 and a total depth of 3, which means that at a depth of x, we have the rest there is 3 minus x. Okay, so we're going to make some similar triangles. Okay, now what we really want to know is the width there. Okay, so the way we're going to write this is we have 8 to 3, that is our base to our height, is our base to our height. So w over 3 minus x. Okay, so those two are definitely related. They are similar. Okay, so now if we cross multiply, we have 3w. Now we're trying to find what w of x is. So we want our w in terms of x. So 3w is 24 minus 8x, which makes w equal to 8 minus 8/3 x. So our w of x is 8 minus 8/3 x. All right, so plugging that into our formula, our force is 62.4 times the integral from 0 to 3, okay, and that is because we're wanting to know it's full of water, and so from the bottom to the top is 3 feet, okay, of 8 minus 8 over 3x times x, okay, our s of x times our w of x dx. Okay, now I'm going to leave that, the evaluation of that, since it is a polynomial, to you, and that is going to be equal to 748.8 pounds. Let's see, the force. The force is going to be in pounds, so there we have that. Okay, one more similar to this. A water trough is 12 meters long. It has ends shaped like inverted isosceles triangles, with a base of 6 meters and a height of 4 meters. Find the force on one end of the trough if the trough is full of water. Now, it's worth noting that in the last problem, we didn't even really need the whole trough. We didn't need a picture of the whole thing. All we need is an image of the base. Okay, so the water trough is 12 meters long. That ends up being irrelevant because we're concerned with the ends. We have a base of 6 meters, a height of 4. Alright, so we are going to need some similar triangles eventually, but s of x, our depth function, is still x, because x is what our depth is. Our rho, our density, is 9,800 newtons per meters cubed. Okay, now our width function. That is where we're going to have to set up similar triangles. Alright, so that is going to be, we've got 6, and at a depth of x, we have a remaining portion of 8 minus x, or 4 minus x, and we don't know our width. So that will be 6 is to 4 as w is to 4 minus x. So that would be 24 minus 6x equals 4w, And W is 6 minus 3 over 2x. 6 minus 3 over 2x. So that puts our force. Okay, so there's our width function. So our force is equal to the integral from the bottom to the top, 0 to 4. The trough is full. Of 6 minus 3 over 2x times x dx, which is going to come out to a force of 156,800 newtons. Okay, and I've said this a bunch of times here now, but make sure that you are rewinding, that you are making sure that you understand what's going on. That way when you get to class, if there are things you don't understand, you can ask about that. So that we should spend our beginning of our class doing that. Okay, that is the end of 2.5.